Hello, my name is Kneller, and this is my biomaterials presentation. Before you read this article, there are a few topics that you'll need to have a good level of foundation knowledge about. This includes the anatomy of the arm and basic mechanics. The anatomy includes bones in the forearm, which are called radius and ulna, and the bone in the upper arm called the humerus. You'll also need to know the names and location of the four major muscles involved in flexion of the elbow, which are the biceps brachialis, brachioradials, and the extensor carpi radialis longus, shown in the diagram here. Anatomy was briefly discussed in the module taught in second year by Victoria. For the mechanics, you'll need to be able to interpret a simple force diagram where the muscles apply a resultant upwards force and the downwards force is provided by the weight of both the forearm and the object in the hand. And bending, which includes how to compute a simple bending moment of a system using the force formula times displacement, and also able to recognise normal and shearing forces. This was taught in third year module biomaterials by Luca Marcelli. The aim of this article is to estimate the stresses in the forearm, including bending caused by holding a weight in place against the force of gravity, with the forearm in a position of horizontal elbow flexion. This article calculates values often and compares them to known values to assess accuracy. The given lengths for both the radius and humerus were measured from 8 human male arms. Mean value of the radius bone was 24 centimeters compared to 32 for the humerus bone. Obviously, there are more bones and muscles involved when the forearm is in supination, but for simplicity, this article ignores them and only focuses on the major ones with the largest lengths and forces. The positioned weight is 6 centimeters away from the stylo process of the radius in the distal direction, which is in the hand of the user. As you can see in the free body diagram, the muscles all apply an upwards force in some capacity. You need to resolve each one and find the resultant force in the y direction. The article includes a value F for some equations, which is the force per unit of muscle, and in this case, 20 newtons per centimeter squared. The value F is identical for all muscles involved, which isn't entirely accurate, as many different articles have a wide array of results, ranging from 17 to 28 newtons per centimeter squared. This could cause uncertainty later on in the experiment. This is the formula used to solve for weight when F is specified as 20 newtons per centimeter squared, and an L-top value, which is the distance from the elbow to the line of action, of 31 centimeters. The formula is used by adding the data for muscle length and angle, which is shown in the table on the right. The formula shows that the weight comes to a value of 120 newtons and an equivalent mass of 1.2 kilograms, or a moment of 37.2 newton meters. The moment formula is m equals fx and was taught in the second year module biomechanics. The values provided here, however, are half that of the expected result from a paper by Klein. However, this can be explained by a couple of factors, which include the oversimplification of the value f, which is not fully reliable, and there's even been research to show that the force exerted by different muscles cooperating in a single task have non-identical values. Another factor is the error in the length of the muscle, which changes depending on the angle of flexion to the elbow, and is very complicated to work out, so for this article has been ignored. They've also ignored several small muscles which contribute to the process of supination and may have something to do with the small weight values. Values in the y direction are calculated with this formula here. The constant values of F and weight are used along with the muscle-specific values of PCSA and theta from the table on the previous slide. The joint reaction force of X and Y can be calculated, which come to 304 newtons for X and 377 newtons for Y. Both these values are a lot higher than they need to be, and this is typical of most joints in the body where the muscles are working at a mechanical disadvantage, meaning through a short lever arm. This means that muscles are required to produce a much larger force than they would do if they did not have a short lever arm. The maximum bending moment is easily calculated as 2,323, as shown on the graph here. To work out the bending is more complicated than the forces. To overcome this, the article first attempts a simplified method of presenting the arm as a single uniform beam, rather than the two non-uniform bones which actually make up the forearm. A hollow beam of circular cross-section is presented to have an inner and outer diameter of di and do. According to a study of the diameter of 86 human radius bones, it was found that the internal diameter is half that of the outer bone diameter. So this formula can be used. The ratio of inner to outer diameters equals 1/2. So we can obtain that the outer diameter is 1.4 and the inner diameter is 0.7 centimeters. This is strengthened by a study involving calipers to measure the lengths of the bones. With these measurements, you can calculate the moment of inertia and area. This was taught to us in biomaterials module from 3rd year. The ratio of the maximum value of the first term to the value of the second term is shown in this formula, and when the value of 2,323 from bending moment and 304 from compressive internal force is added, the formula comes to 35. So this shows us that the stress formula, which is shown at the bottom, the axial force is negligible, and so we can ignore it. Now consider the arm in a more accurate double beam system, where it is stated that mx equals mux plus mrx. However, this does mean that we can no longer use the simple Euler-Bernoulli beam theory, as this doesn't work for two beam systems. An assumption made is that the radius and ulna are sized so that the maximum stresses will be approximately equal. This is given strength by the idea that the bone remodels in response to stress, meaning that the formula can't work. At the point where the bending moment is at its maximum, both bones have the same diameter, so it's safe to assume that the bending moment for the radius is half the total forearm, meaning we can simplify the equation to this one shown here. The value of stress is 4,600 newtons per centimeter squared, and is accurate as the predicted Young's modulus for this system is 17. This leads to a strain value of 2,700 microstrain, which is within the predicted limit of 2,000 to 3,000. In my opinion, the article was successful in working out the forces involved when a weight is placed in the hand of a patient in elbow flexion. The article was clear to follow and explained how to use the formula provided very clearly. Simplification of certain areas made sure that people with limited experience could follow the calculations. However, the article did make a lot of assumptions, which may have slightly impacted the overall accuracy of the results. An example of these assumptions is ignoring a more advanced anatomy, such as smaller muscles and bone-to-bone connections, such as interserous membranes, which are a key factor of force transmission. But overall, as the values are close to known accepted ranges, especially the strain value of 2,700, I would consider this study successful. Okay, this was my presentation. Thank you for watching.